My sincere thanks to Professor H.R. Kataria, our Dean, and Professor Vipul Kalamkar, our Head of Department, for their kind, encouraging, nice words. Thanks are also due to my colleagues, Dr. Professor D.K. Patel and Professor Rupal Shah for coordinating this webinar. I'm so happy to see that there are a lot of foreign participants enrolled for this program. Although I can't see them personally, I hope all of them have joined already. I'm also sorry to say that we could not accommodate all of you for the Zoom meeting, but we have made the arrangement for virtual live streaming in Facebook as well. I hope all of you have joined. Good afternoon once again. Okay, dear participants, this presentation is actually meant for students of statistics and mathematics, maybe in undergraduate or postgraduate. I'm sure that this presentation is also useful for professionals and consultants, even engineers also. Because the concept which I'm going to discuss, I'm not only going to discuss, I'm going to illustrate the whole working principle of central limit theorem. I'm sure you might have already visited, when you heard this topic, you might have visited the website for literatures on central limit theorems. There are many literatures available on central limit theorem on the website. Even there are a few videos also available. Even I happen to see a couple of videos. As I have seen that the theory is explained with some pictorial ways and all. So how come this is going to be a different from those presentation? I could say that this is going to be completely a kind of demonstration, which I'm going to show it on Excel software. So I expect that the participants will have at least some bare minimum knowledge of statistics and a knowledge of Excel software at least. This is the only requirement for this particular seminar. So without wasting too much of time, I will get into the presentation. I have a few slides to show you. I just want to make your base clear. Why do we want to go for central limit theorem and what is the importance of it? You know, with the advent of big data, data analytics, you know, with these new subjects coming up, statistics is now shaping up in with new features and all those things, you know. With that, the many theories of statistics are going to get a new look, new flavor. People are using it. So this is one, because I happened to see some papers, research papers, where related to big data and data analytics papers, where people are talking about central limit theorem in a peripheral way, without gaining much or without showing the real importance of it. But the people are finding the importance of central limit theorem if they really wanted to make some headway in their research. So let me start with the research, the slide presentation for a while. There are a few, so I don't want to make you, boring. So let us see this presentation first. I hope all of you can see this presentation. Okay, I put it in the presentation mode.
Yes, we can. Yes, we can.
Okay, that's fine. So, okay. So we quite often come across with many statements like this, you know, many situations and contexts we talk about normal, normal, normal. So just go through this, the statements which are shown there. They're very interesting. You know, many often we make these kind of statements, knowingly or unknowingly. If the answer is yes, definitely we can have a great sigh of relief. But what about the answer is no? The third point you can see, when can we expect the COVID-19 virus infection is going to be normal? This is what is the common feeling everybody is having now. Everybody is thinking when it is going to be normal. Nowadays, people say that the infection is growing according to exponential distribution. It is true, very true. And when it is going to be normal, this is what everybody is concerned now. The same way you look at the other questions also posed there. So what is the meaning of all these? So if the answer is yes, no problem, we are okay, we are on the safer side, we are through. If the answer is no, we are concerned. There is a problem. We ourselves start doubting. What is the problem with the process? What is the problem with the delivery? Why it is delayed? What is the problem? What could be done to make it normal? How can you bring it normal? So these are the sentences. These are some of the off-quoted knowingly or unknowingly, which often we make as something which may be concerned about somebody else, may be concerned about ourselves. So this is a very important thing. So what do you mean by this normal? What do you mean by control? What do you mean by the stable? What do you mean by consistency? What are all these talking about? So no doubt it is talking about normal. Okay, look at this graph. This graph is about the body temperature of patients, maybe patients who are identified for COVID-19, maybe in the initial starting point. Suppose around 400 patients. Body temperature is, recorded, and a histogram is plotted. You can see most of the time, our normal temperature lies between somewhere around 97 to 99. That is how it used to be. And very few people have temperature less than that, 95, 96, even less than that. Some of the people have temperature over 100, 101, etc. etc. The patient is really having fever, definitely it will be more than 101. Can be 102, 103, or something like that. So normal is something which we often make sense about it. We know that when it is normal, we are on the safer side. So why it is so important then? It is bell shaped, as you can see from the graph. It is bell shaped, symmetric about the mean. You can see in the middle. Okay, it's considered to be an ideal distribution for all decision making. That is very, very important. It's a very important sentence. All business people working in any area of service, maybe it's production, service related, or automobile related, or transport related, anything. So people make a base as a base for decision. Everybody wants a normal distribution. Everybody wants that the process to be normal. If that is the case, then they can think of what is the next course of action. And this is generally practiced. Have you ever heard anybody keep the base distribution as exponential or some other distribution? All other distributions except normal or maybe t, all other distributions are skewed, either skewed to right, skewed to left, or there are problems. That doesn't mean that we are not using those distributions. They also have their own specific application areas, but normal distribution is considered to be the base of all. Because it is considered to be the distribution with controlled variation. You look at SQC techniques, statistical process control, quality control techniques. We always base normal as the distribution, because still normal also has variation. When you say 3 sigma covers the 99.7%, it means still there are about 0.027 variation on either side. So to have a future course of action, we should have a say-based distribution. That is where the normal distribution comes in. It's considered to be a stable distribution. Some people say it's a stable distribution. Stable, don't confuse with the stable. It's a family of distribution. Stable distribution is a family. Here I mean consistent distribution. So we want a consistent distribution. Normal is the one. It's also considered to be quality distribution. These days, most of the professionals, quality professionals, Six Sigma, Lean, or TQM or ISO people, everywhere, everybody consider this normal distribution as a quality distribution. Yes, of course, it has a quality connection. That's not the time. It is not the time to discuss all those things. So please understand from the philosophical point of view also. So normal distribution is considered to be a universal distribution. That's the reason why it's considered to be a universal distribution. And of course, it is characterized by two parameters: mean, generally notated by mu, and standard deviation sigma. So please note these two, see some important points: mean and standard. So these are, or maybe variance, square of standard deviation. So, and the mathematical expression is shown here. You can see f of x is equal to 1 upon root 2 pi sigma e power minus infinity, and which ranges from minus infinity to plus infinity. There are two graphs shown there. You can see one graph, the first graph, where mean is same, standard deviation or variance is different. And that's the reason why the shape is different. You can have one with high peak, then moderate, then flat, but the mean is same. That's, I kept a mean at 100. And the variance is different. That's why the shape is different. And look at the second graph, where I kept the shape, variance same. That's why shape is same. Whereas mean is different, so mean is deviated, the target. So business people say mean as target. So these are the way how the distributions looks like. Now comes, what is the catch? We always talk about normal distribution, we want normal distribution, etc., etc. So this is very, very important. To understand central limit theorem, you should know normal distribution the way it should be. Without the understanding of normal distribution, you cannot understand central limit theorem. So normal distribution has many interesting properties which can be proved theoretically, which can be shown practically, which can be illustrated practically. So this is very, very unique in that sense. There are no other, those distribution where this can be done. Theoretically also we can have constructs possible. Practically also we can have constructs. So let us see what is the catch here. So if you are doing sampling based on normal population, then definitely almost all characteristics will follow normal distribution. There are some exceptions as well. Okay, I'm not discussing those things, but by and large, most of the characteristics will follow normal distribution. And of course, you all know that sample mean follow a normal distribution. Sample median also follow normal distribution, but parameter will be different, that's all. Joint, marginal, conditional distribution also follows normal. We can have proof, theoretical concepts are possible. So now comes the very important point. What is sample and what is population? So here at least I have to say something about population and sample. So sampling is the essence of the whole statistical decision making. So we'll have to see what is sample. So population, what you can see on the left side, and sample is what is seen on the right side. From the same population, some samples, the red colored, they are the samples. So, and every population, there are characteristics, they are called parameters, and sample characteristics are called statistics. So it's now a play between statistics and parameter. So every population, in statistics, all probability distributions are called population. So we call normal population. Instead of normal distribution, we can also call normal population. Similarly, binomial distribution, you can call binomial population, Poisson population, geometry population, exponential population. So in probability theory, the population is as good as the distribution. And when you have suppose even if it is not normal, at least you can see the graph, how a population graph looks like. Since we are sampling from that population, definitely the sample graph, the histogram also looks like. They also retain the same characteristics. So population characteristics, there you can see mu, sigma square, sigma, etc. So please stress on this kind of notations. I am going to use at least one or two notations from here, and similarly from the sample characteristics, I will be using the notation x bar, s square, etc., and sample size small n. So this is very, very important. So even if you are not sampling from normal population, doesn't matter. The sample will definitely retain the characteristics. And with that, we start with the inferential parts of statistics. So what is inference? Inference is the way of, it's a process of characterizing the population based on a sample of observation. You can do estimation, can do hypothesis testing, you can do many other things. You can use descriptively also, we can talk about the population characteristics. Then estimation, again, you can have point estimation, you can have interval estimation. There are many ways now inferential statistics, and everybody wants statistics because of these reasons. Inferential statistics, inference is what we are doing. All you look at any discipline other than statistics, even social science people also do statistics. They also want inference I mean drawn out of sample. Commerce people, management people, and they also engineering people also do all kinds of statistics. I mean, they do inferential statistics. So what is the speciality of all this? If you look at inferences, whether it is estimation, hypothesis testing, or any other inferences you talk about, Bayesian inference, this is another area which is coming up. So everywhere, if you see, most of the time the statistics which come. So when I say that we do all the inferences based on sampling, means the sample characteristics will be drawn out of that. And those sample characteristics are most of the time either mean based or sums based, either summation xi or something based on, or summation xi by n, that is mean, nothing but, or something else, can be median also, no problem. In non-parameter test, inference, we use median as one of the estimators. Now, all this mean, median, mode, they are central measures. So, but still we know the importance of mean. Mean being a universal measure because it satisfies many interesting properties, it's considered to be a universal measure of accuracy. So that is the reason why we go for sampling, and sampling most of the time leads to either sums or means or something like that. So first thing you should make it clear is that sampling is an integral part of all statistical decision making. What type of sampling we do, what kind of sampling we do, when we should do sampling, all those issues are, another part of classroom teaching. That's I'm not going to discuss it.
Next one is hyperbolic tangent function.
Somebody's asking some questions, or I don't know, some voice is heard. I don't know what it is. Okay, let me complete it. If you want to ask some questions, you can even have chatting, or you can have some questions maybe at the end of the session. Okay. So let us now see important part. Regarding normal population, no problem is not normal. Suppose we are working with non-normal distribution, then what is the purpose? Okay, so in statistics, as I had already mentioned, the population is, are always, or distributions are always called as populations. Now, suppose sampling is not done from normal population, then what is the distribution of sample? Although we call that, although we say that it is going to, but real situation, getting into normal or getting any process into normal is going to be, difficult. Okay. So there comes the importance now. If you are working with a non-normal population and you are sampling from there, how do you get into normal is also a question, a very important question. And what kind of characteristics we can have. So that is another point of discussion here. So yes, we do often a kind of transformation, standardization, and normalization techniques. So this is how you can reach to normal. That's not a very big issue. People do it. Quite often people do. Either standardization, sometimes normalization, sometimes transformation. But there is no guarantee that it is going to be normal again. For example, transformation. Many often people make a logarithmic transformation. Even these days, the coronavirus infection cases are plotted in two types. Either on the real data, which is maybe raw data, which is plotted maybe in the exponential group, and sometimes people plot it in a logarithmic scale. And you know, logarithmic scale stabilizes some amount of variation. The same way here again, getting into normal, there are ways, but there is no guarantee. So if you are working with a non-normal population, and if you want a good sample characteristics, then get into normal through normality plot is also there. Yes, there are many ways to get into plots are also possible. You can use standardization with the mean minus divided by standard deviation. That is another way. Then normalization, you check for, you plot the a box plot and see whether there is any presence of outlays, inlays, remove it, then redraw, etc., etc. So these are all manipulation techniques actually. Standardization, normalization, transformation, they are all manipulation. Data remains the same, and we do some kind of transformation or this thing, etc., etc. So there is no guarantee that you will be back to normal. So now comes to the point again. How do you get into normal? So this is my the importance of my talk today. That is central limit theorem. Okay, as I mentioned already, most of the times the estimators or maybe the statistics comes to be in the form of sums or means. You can see, you can write down in each concept, you write down what is going to be the estimate or the statistics which you are considering. Is it going to be a function of sums? Is it going to be a sum of means or something, some function of means also it be possible. And they're all observations. Mean sum is nothing but sum of xi's, x1 plus x2 plus etc. xn. And if you divide by n, that is going to be means. So you can see that 70 to 80% of the time we are working with means or sums. So we are now through with one characteristics. Now the question is, how is going to be get the distribution of that? So mean is considered, or mean, and another name is average, is considered to be one of the best measure of accuracy. Now the question is there any distribution of sample means? That is what we are going to answer. So in a way, central limit theorem points towards the distribution of accuracy. So it's a perfect balance now. So accuracy measure, mu is, all central tendency related measures are called accuracy measures, and all dispersion measures are called the precision measures. So we have now mu as one of the representative from the accuracy measure and sigma from the. So these two will connect the central limit theorem. That is how we are going to take up further now. Okay, let us now see this theorem, how technically this is going to be explained. Now I am sampling, as I told you, I am going to sample from non-normal distribution. Okay, or non-normal population. As I told you many times, distribution or population, they are synonymous. I can use both the terms now. Now carefully watch this particular slide. I'm going to have the same kind of data generated from some distributions. Then I will explain how the central limit theorem works. Okay, so you can see that there are sample 1, sample 2, sample 3, etc., etc., sample k. There are k samples. Okay, I'm going to have k sample. Maybe you can say capital X1, X2, X3, etc., Xk. I have k samples. Now for first sample, I have observations, maybe data points. I can say data points or observation. The first sample has points, data points x11, 12, x12, etc., x19. That means the size of the sample here, there is n. Similarly, sample 2 also have n samples, x21, 22, etc., 2n. So I have another size of sample n, call it as sample 2. The same way, I have k samples, each of size n. I hope all of you can understand that. It's a very simple thing. Please note, it's a very important table. Now, since I have a sample form, and note that all the samples are independently observed, and they are all from the same distribution. So I will put it in the form IID. I stands for identically distributed, or maybe independently distributed and identically distributed. The same sample from the same population. I am generating samples from the same population. Okay, I think that is clear. Now look at the first sample. I can have so I have some data points, each of size n. For sample 1 also I have size n, sample 2 also I have size n. So I will take the mean. That's the best one. You're talking about mean, or you talk about anything. Right now I will talk about only mean. So I can very easily compute the mean of x1, the sample 1, that I call x1 bar. Similarly, the sample 2 mean I call it as x2 bar, then x3 bar, like that, xk bar. Now the question is, or you can say what the central limit theorem aims for. The question is now, what is the distribution of these x1 bar, x2 bar, x3 bar, x4 bar, etc., xk bar. Now that is now a random variable now. I call it as x bar. Let me put it in the x bar is actually that vector, that means of vectors, or vector of means. That's the best way to say. What is the distribution of x bar? This is what the central limit theorem is going to give you. So here is the general theorem, statement of the theorem. So please note that I have started with a general non-normal population, some unknown population, okay, with some mean mu. There also I give the mean, the representation mu and variance sigma square. Don't get confused with this mu and sigma square as the mean of the standard deviation. I'm just giving a notation for mean as mu and variance as sigma square. Okay, this can be from binomial, can be from exponential, can be from any damn distribution. Now 200 sub-distributions are now available in statistics. Okay, let us see the statement in general. I'm quoting that theorem in general as the way it was quoted in reference books and textbooks, etc., etc. Okay, let us see the statement. So very important. Now, if x1, x2, etc., xn are n random variables from any population, it is red mark, any population, which are independent and having the same distribution with mean mu, standard deviation sigma, then as n tends to infinity, the sampling distribution of the mean x bar is approximately normally distributed with mean mu and standard deviation sigma by root n. And that sigma by root n we usually call, because it is the sample standard deviation. This standard deviation sigma by root n is actually the standard deviation of the samples. And that's why it is called a standard error of the mean. So the standard error is nothing but this standard deviation of these samples. And the technical statement is, in that case, x bar is approximated as normal n of mu. Mu is the mean, sigma square by n is the variance. Or if you standardize, if you take minus x bar minus mu, then follows n0 and sigma square. Again, further standardization with the sigma by root n, if you divide it by that, that will follow n01. This is how the CLT, the central limit theorem, is stated in different books and reference books and or the literatures. Okay, one can go for any kind of one. All the three expressions are same. All the three ways presented are same. Okay, now again go back to the same table again. You look at the x1 bar, x2 bar, x3 bar. So x1 bar is the sample mean of the first sample. X2 bar is the mean of the second sample, like that. So we are looking for the distribution of that. So you can also have here reframe the sentence as, suppose if x1 bar, x2 bar, x2 as xn, xk bar are n independent random samples from any population. That way also you can interpret this theorem. So there is no problems. So I will now going to show you a similar kind of table prepared, generated through Excel software and from some distributions. So I will show you two illustrations. If time permits, then definitely I will go ahead. Okay, let us see how it works now. So again, okay, let me go again show you the same table again. So I'm going to generate k different samples, each of size n, and then compute the mean of each sample, and then I will look for what is the mean. And that should go according to this statement. Its mean should be mu and standard deviation should be sigma by root n, and we call it as standard error. So let me start with the uniform distribution. So here is the uniform distribution. As you all know, even from the first year undergraduation also we start with, we teach this kind of distributions. So this is the density form of the distribution, 1 by b minus general form, a to b, and mean is a plus b by 2. Variance is sigma square is b minus a whole square by 2. And the square root of that is standard deviation. Okay, so please recall this. I'm going to use this and we'll discuss that. And can easily generate the samples from X is from this notation. Sample generation is a matter of statistics principles. We call that probability integral transformation. What we do is we equate the distribution function of the population or the distribution with a uniform random sample, and then express X in terms of the uniform random sample. Here U stands for the uniform random sample. Okay. Now let me minimize this particular presentation here. Okay. I will minimize this presentation here. I will go to another sharing. I'll go to directly the Excel file. Sorry, not Excel file. Let me go to Excel. I hope you can see this. My colleagues, can you see this Excel file open?
Yes, sir. Yes,
Okay.
sir. Yes, sir.
Okay, 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 okay. Let me remove all this. Okay. I'm sure all of you might have worked somewhere or not, the Excel softwares. So this is how the organization of Excel software, the spreadsheet. You call it a spreadsheet. Okay. So what I do is I will have a table which I had already shown you in the presentation. I will generate K samples of uniform. Okay. And compute the mean. Okay, let us generate the samples. Now there are many ways to generate random sample. Uniform random sample is very easy to work with. Okay, let us start with one. So let us now say what let us say what you want to have your A as. So let me say A is equal to say 10. Okay, or and B as equal to say 30, whatever may be. So let us say I want to generate the samples from 10 to 30, uniform random sample from 10 to 30. So what you can do is, okay, let us begin with a very simple one. This will be a generalization. So I will start with A is equal to 0 and B is equal to say 30, for example. I will start with this. Okay, let us now start with say, okay, so just put this, just say random in the expression, give the expression random, okay, random into 30. So you will get random samples of uniform from 0 to 30. So this is the first random sample from 0 to 30, the first random sample. So if you copy, you will have a different samples. They are all different samples of uniform from 0 to 30. So this is the one way. Okay, and if you copy this, you will have a series of random numbers generated automatically. So because random, this RAND function, random function, it's Excel function that generates different numbers between 0 to 1 every time. So I multiplied by 30. That's because I use that formula. If you recall that formula of random generation, A plus B minus U times U. Here A is 0, B is 30, so it amounts to be random 30. Okay, this is one way of generation. Now, I would prefer this one, but there is another way of generating random sample. I'm going to the next sheet. Okay, and just to show you how it can be generated, go to data analysis. There is a panel called data analysis panel, toolpad panel. So there you can see random number generation. Just say okay. Okay, so now decide. Now you can say uniform, no problem. How many random variables you want to say? Suppose you want to say so for example, 10 uniform random variables, and of size what? What is the size of each random sample? Can be 5, can be 10, 30, or etc. And where do you want to have the number generated? Give some space. Not necessarily that you have to give the whole space, etc. So I'm just saying, okay, this is one way. Now you see, this random number will not change for any action, whatever I do. For example, I'm going back to the previous the sheet. So even here, if I say, now what you understood from this one, now let me, can I minimize this? Sorry, I will go to, sorry, where I will go. Okay, so I can call this as my first random variable. I can call this as my second variable. Please watch the screen. The random numbers are changing every time. X3, like that. I have K samples. You can go on naming X1, X2, X3, etc. And if I go, I'm going to the next sheet, which I had shown the other way of generation. Here, if I say X1, I can say in the same way X1, but here random numbers are not changing. Okay, so there is no problem. Both will give you the same conclusion and everything. So don't bother about, but I would prefer this one because you can see the changes every now and then. Okay, so let me take it off. Okay. Okay, so this is how I have generated the random numbers from uniform sample. So what the theory says, Suppose this is your first sample x1. So what is the size? For example, here there is the first entry is in the column C2 and it is in 16. So the sample size becomes 16 minus 2 plus 1, that is roughly 50. So your sample size, the first sample is of size 50. Similarly, second sample is also of size 50. Similarly, x3, x4 like that. So what I will do is, now this is a small sample, we may not be end up in a good result, but we'll start with this one. Then later on, we will extend it for a large sample size. So let us compute the mean of this. So I'm just computing the mean, say average. So average. So just mark this. So this is the average of this particular variable, and I'm copying it to others. So I found the average of all the random variables. So I have only very few random samples. So what is a random sample? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So my samples, I have 13 samples and samples each of size 50. So please note this, I have just written here. So for any action, you see the random samples are changing. So don't worry about it, nothing will happen. Okay, so I am now going to draw the graph of this. These are sample mean. This is just like your table which I had shown you. Okay, I have 13 samples here instead of k is 13 here, and sample size n is 15 here. So I have the sample mean also ready. I will now take this whole thing to I want to draw the histogram for it. So drawing histogram in Excel is possible, but it needs some time because you need to specify the bin range and everything. So what I will now do is I will just transpose this to make it a column variable. Okay, so I will go to paste special. So I will just say transpose. I will just say values. Then I say okay. So I just got the same row wise. I am now in column wise. This I will copy. I will take it into, say I'm going to minimize this. I'm sharing another screen with you, that is MINITAB. Okay, so this is the MINITAB. Okay, I'm copying the same thing. This is also just like an Excel spreadsheet. Okay, so where is, sorry. Okay, so I'm just copying that variable here. I can copy anywhere, no problem. So I'm copying here. Okay, now let me draw the graph of this. Okay, this is how, I don't know how many of you are familiar with the MINITAB software. This is how the environment looks like. So this is just like there are 3 panels actually. This panel is the just like a spreadsheet. And second window is the output window. And those who have worked with SPS, they are, I'm sure they are, I mean, a similar kind of panel, they could see there also. So there's a histogram here. I'll just go for the histogram. Okay, I already, by default, it is simple histogram. I will just say okay. And I will now get, say, I will, this variable I kept. You can see that it is in C8 column. So I just select that to the graph variable panel. So this moved here. You can double click also, you can come here. So now simply say okay. Okay, so you can see that that mean is now somewhat going to be normal. It's very interesting, not bad. Although it is a small sample with a k variable, 13 variables with a file size. If you increase the sample size, definitely it is going to be very close to normal. Now we will have to see whether really central limit theorem works here. So let us see, let us go back and see what is the statistics here. So we know what is the population. So we started with a equal to 0, b as b equal to 30. And we know that population, let us first write down, population mean is actually a plus b by 2. That means 30 by 2. That means it is 50. So this is, let us complete the population related. So population standard deviation is actually, a variance is b minus a whole square by 12. So I'll have to take the square root of it. So which is equal to SQRT of B minus A is 30 minus A 0, that is 30 square, that is 900 divided by 12. So this is your standard deviation or the population standard deviation. Okay, let me also compute here population standard deviation divided by square root of n. That is nothing but standard error. So I will now say SD divided by SQRT of n. Let me compute that first. And then, okay. So that is nothing but sigma by root n. So this is nothing but sigma. This is your sigma divided by, and your sample size was n is equal to 50. So sigma by root n. So SQRT of n is 15. Okay, so it's all everything. So population related characteristics, everything is ready now. Let me compute the mean of this. So this is your, please note, this is your sample mean of each samples. We have found the distribution is almost normal. Now we have to see whether it really follows the central limit here. So that is where now I will compute the mean of this. Just compute the sample mean, sample related characteristics. So let us say mean here, let us say standard deviation here. So let us say, what is the mean here? Average of, average of this. Okay, so I hope I have not made any mistake. Okay, 13.83 is roughly 14. 14 and population mean, you can see almost, okay, it's a very small, but still we are able to get into normal, at least near to normal. So 13 point something. Let me compute the standard deviation of this sample. So we can have STD, standard deviation. Okay, so we can have the standard deviation of this. So it is coming out to be 2.4782, and compute this. And please make the comparison. The ST, this is nothing but the standard error, and this is the standard error as per the theory. So they are matching almost. It is 2.47 and this is 2.23, almost matching. There is no problem. I hope you can get something about of what I did now. Okay, so if you increase
Hello,
the
sir, the screen. Hello, sir. Sorry to interfere.
Yeah.
Sorry.
Okay.
Whatever
Okay.
calculation part you are doing is in Excel. You are doing right now or MINITAB?
Oh, I am doing in
because
Excel.
We are not.
You can see now.
No, Excel is not visible right now. Your MINITAB is open.
Oh, MINITAB is open. Okay.
Yes,
Okay. I have just taken directly from. Okay.
Yes. Switch the window.
Let me go to the presentation. Where is? Okay. Let me share the Excel file again. Excel is here. Okay. Thanks for reminding. Thank you very much, madam. Okay. Can you now see the Excel file?
Yes, sir.
Yes,
okay.
Sir.
Okay. Now let us compute. Can you see this population mean I have computed? That is, we know that it is, we have generated the sample from 0 to 30. So the population mean is A plus B by 2. Is that correct? Can you see this one? Rupal?
Yes, sir. Yes,
can
sir.
Yes, sir. Here,
just little bit few steps if you can repeat, because the audience was not, I mean, the participants were not able to see your Excel screen. Meanwhile,
I'm repeating again. I'm not, okay. So sorry, I'm removing all those things. I'm repeating it again, no problem. Okay. So, we started with the population, uniform random sample or uniform population with initial, I mean, A as 0 and B as 30. So, what is the population mean? Population mean is going to be A plus B by 2. That is 30 divided by 2. That is 50. Is it okay? Madam? Rupal, is it okay?
Sir.
Okay.
Yes,
okay,
sir.
Fine.
Yes,
so
sir.
Let us see what is population standard deviation. Let us compute the population standard deviation. And we know population variance is B minus A whole square by 12. So population standard deviation is nothing but square root of that. So equal to SQRT of, okay, B minus A means 30. 30 square means 900. 900 divided by 12. So this is the population standard deviation. I hope it is correct. Let me also compute population's SD divided by SQRT of n, because in the theorem I had mentioned the population, the standard error as sigma by root n. So I just written that okay. So population standard deviation divided by square root n. So this is the standard deviation sigma divided by SQRT of n, and your sample size is 50. I hope it is clear. So this is how the standard deviation is coming out. Now again, let me compute sample related informations. Okay, let me compute the sample related information. So sample standard, because I have done the sampling. I have the mean now. So I will now see what is the mean of the means. Mean is equal to the mean of average of this. It's almost same, 15 and 15.8228. So they're very close, no problem. That much approximation is possible because we have started with a very small observation, sample of observation. So let me compute the standard deviation of this particular sample. This as the sample means. So that should match with the population standard deviation divided by square root of n. That is sigma by root n. That is going to be sample. So let me compute the standard deviation of this sample means. So STD, standard deviation, okay, of this 2.38, and here it is 2.3. Almost through. I hope this is understood. Okay. Now what I will do is I will now start with another sheet. Quickly show. Now I'm not going to discuss very much in detail. I'll just start with let me remove all these things and come back. Okay. My A is going to be, say, I can have 10 and B is going to be 50, for example. So I will have to have now samples. So let us generate samples from, okay, generate from uniform 10, 50. So what I will do is, this is nothing but 10 plus 40 times random. This will give me a uniform random sample from 10 to 50. Now this is, as I told you, once more also, and suppose you may be thinking why I did that. What you can try is, instead of pressing enter here, press F9, the function key F9. What you get is a random number fixed for that particular request. Now if you copy this will only the same number will copy. It's not changing. So that's the reason. So you can make a control also. If you want to have a different number, again you will have to go for that the statement. So 10 plus 40 times RAND this and F9. Press F9 along with that, you get another random number. But this is a tedious task. That is the reason we can either go with the data analysis tool pack where the random number generation is shown. But that again is not going to change every time. So this is the reason why I prefer, I told you already, I don't want that every time should be return statement is given and the number is kept constant. So I want every time a number change. So that changing, that random number, with that change, the whole analysis is not going to change. Okay, so I will now again make a statement. Okay, that is 10 plus, that is A plus B minus A is 40 into RAND. Okay, so I will just press it. So I have now, if I copy this, so let me have a good number of samples. For example, say let me have say 303. Let me have say sample size is 300. Okay, let me copy it to say yes. Let us go for AZ, B, or okay, A, B, A. So I have now. Let us understand what is this. So I have now around 25 samples, 25 different like this. If I say this is X1, this is X1, x2 like that. I have now up to AZ column. I have kept it as I have AZ. You know, it is going to be, sorry, not 26. It is going to be 52. 52 and plus this one. I started with third column, so it is going to be roughly 51 samples or so. Okay, so let me magnify. So this is how the samples, I'm sure this is not going to be so visible, only to show you. So I have now around 52 samples. And what is the size of it? So size is 2. If now again another point which I'm going to discuss later part is, if you say that column wise each one is a sample, column wise is a sample, definitely this is going to be a sample row wise also. So I will show you that execution also. I mean CLT applied to that also later. Okay, let us now understand this is the, this one. So I have now x1, x2, x3, etc. There are 51 columns or so here, 51 random variables. Each of them are generated from uniform. They are IID because identically distributed. Magnify this again. Let me again magnify this. Okay, so you can see the sample is somewhere around 303. So this is the size. So again, how do you treat this spreadsheet? That will depend on what size and what number of variables. Right now, again, I am going according to the presentation which I had shown you. So column wise, I will say each column is a variable now. So this is x3, x4, x5, like that. You have around x51 or so, f52 or so. That's okay, no problem. So now each row is now a sample, is a data point. This is the first data point, second data point, third, etc., etc., etc. So I have now. So what I will do now is I will compute the mean. Okay, so let me demagnify it. Okay, let me. Okay, this is enough for me. I will just compute. So the mean is equal to average of. I can go and drag it, or I know it is going to be in D3 to D303. D03. I hope it is correct. Okay. So this I will copy it. So I have the now mean computed for all. Okay. Now this I will again copy it. I just want to transpose this to make it a column vector kind of things, column element. Okay, so here I will go to make it transpose. So I will have to go to special, paste special. There you say transpose. Take only the values because it was based on a formula. So let us make it as okay. So I got now this as a all the means now. So this is the mean of all samples. All those, how many samples were there? 52 or 51 samples. This I am going to copy. Now I'm changing the slide again. I mean the platform now. Where is my, okay, I'm sharing the MINITAB again. Okay, let me share the MINITAB software again. Okay, so this is the MINITAB software. I'm just copying it. Okay, let me draw the graph. Okay, so graph, I'll go with histogram. Again, the same thing. So I'm showing everything in one by one. So C8. I select, okay, selected, okay. So perfect, normal, almost normal now. So there is no doubt. Further, if you want to have a diagnosis here itself, you can have another panel where here you can set basic statistics. There is a graphical summary here. You get the graph also along with, and then some descriptive statistics also computed there. So select that. Okay, so you have descriptive statistics along with the graph. So you can see this is the mean is going to be 14.881. Okay, let us go back now to our, okay, these are the other I mean things you have. You can have box plot here, you can have confidence interval here, you can have many other things also. Even normality also you can check here. Here p value is here 0.931. It's accepted. So normality is accepted, very high value of p. So there is no problem with that. So let me now again Graphical, actually it's okay, confirm that it's normal. Let me go back to the Excel presentation again. Excel, okay, let me now compute the statistics of this. Okay, so let me compute what is the population characteristics and okay, let me come to the point. So we have generated our population is from uniform, what was that? 10 and what was the uniform? 50, 10 and 50. Sorry. Uniform 10 and 50. We know that this is the population. So what is the population mean? So population mean is going to be A plus B by 2. That means it is 60 by 2, it is going to be 30. And what is population standard deviation? VSD. So square root of SQRT of
Mulidharan,
Ajit.
you have not calculated for C5. You have calculated again for C8. So just people are asking that you also calculate.
Okay.
For
Sorry.
C5.
I did a mistake. Okay. Instead of C, it should be D actually. Okay. That was a mistake. No problem. Please remind me. I will next time. I think I did. Okay. C. Okay. That can be corrected. So for the time being, just see this one. SQRT of square root of B minus A whole square, that is 40. 40 square, that is 1600 divided by 12. Okay. So this is the standard deviation. Let me also calculate SD by SQRT of N. Sample size here, if I am correct, I think it is 303 minus, let me again go back to my 300 minus 2, that is okay. It started from second. Okay. So square root of, so 303 minus 2 plus 1, that is 302. So 302. So this is the, sorry, what happened? Sorry. I have to simply, okay, 300. Okay. So let me compute that. So that is equal to sigma. Sigma is here, 11 point this divided by SQRT of, 302. So this is the standard, what happened? Okay, square root of 302, C13. I hope it is correct. Okay, let me now compute the sample related statistics. So you have, okay, let us compute the sample related. Quickly, I will try here. So it should be mean first. Average of, average of this is 29.90. It's almost 30. So it's perfect. Let me also calculate the standard deviation. Okay, standard deviation of the same means. .650, and here if you see that it is 0.66, it's almost same. So as you get along with number of sample size very large, the approximation also become very close, and you become very close to the normal distribution. I hope this is correct. This is clear to all of you. Okay, now I will quickly, now we don't have any other time for discussion too much. So I will now go to the sharing of the PPT now. I will go for an exponential distribution now. Okay, let me show the presentation again. So it perfectly works. Right? Let us now go with an exponential distribution. Okay, so this is, this is exponential distribution. There are two forms of exponential. Okay, so if you want to keep it, take, sorry, here is a mistake here. This goes here, this goes here actually. Okay, copy paste effect. Okay, so let me show it in the PowerPoint mode. Okay, so let us look at the first form of exponential distribution. So this is the form. DK, can you see? DK, Rupal, can you see?
Yes,
Yes,
yes.
Yes,
Okay,
sir. Yes,
okay,
sir.
okay, fine. So you can see that how the mean and variance. So you can see the mean and standard deviation is same for exponential distribution, whatever form you talk about. Same. And the sample generation is also shown there, as I already mentioned, probability integrated transformation is used. So this is how you can generate. Okay. Suppose I will start the sampling from exponential distribution. So I will now minimize this. Okay, I will go back to the Excel software again. Okay, so this is my Excel software. So I'm back to Excel now. So this is a fresh sheet now. I'm opening now. Okay, so again, I'm going to generate samples from exponential distribution. So let us decide what you want, a mean, for example. So let us say mean, exponential mean, I'm taking it as, say, for example, 10. Okay, so I've generated samples from, say, C2. Okay, random sample. So it is actually minus times minus theta. That is, theta is here, mean is 10 times. Okay, logarithm of natural logarithm. Okay, logarithm of 1 minus RND. 1 minus RND of, okay, 1 more. So this is an exponential random sample from sample with a mean 10. So as usual, now this I will, as I told you, I can generate through some other way also. I can control the change of numbers also. If you press F along with this quantity, if you press F9, the function key, you can control the random sample without changing every time. So that is also possible. So I can have now a good sample. So maybe I will start with around say one more I will have. So I have now sample size is 20. Okay, so 20 sample size. And now let me have around say suppose around A to Z. Let me say A to Z. So roughly 23 samples so I generated from exponential distribution. Okay, so X1. So this is your X1, this is your X2, like that. So it started X2, etc., etc. So you can see that samples are changing every time. I think one should try this kind of sample generation instead of fixing the random sample every time. So you can have some samples change every now and then, for every action in this project. So this is, so I have now about say about 24 samples. I think 24 samples, each of size 20. So let me say I have 24 samples, each of size. So size, that is n, size equal to 20. Okay, so what is going to happen about this? So let me compute the mean as usual. The same way I am proceeding with here also. So I will just compute the mean of each sample. So average, that is the average of this. What happened? Average of this. So let me go to copy this, copy all this.
Only Dharan, there is a comment that take the small sample, so the screen is not visible for bigger sample.
Okay. In that case, I can demagnify this. Is it okay now? How is it now?
Yeah.
Yes, sir. Yes.
Yes.
I think this is okay, no? This is okay. This is okay. Okay, I have now all those mean. I am copying it only to take it into a column wise because I want to draw the sorry, I made a mistake. I will do here. I go for space special. I take values. I will transpose. Okay, so that is transpose. I will copy it. I will now going to share the MINITAB. So where is MINITAB? This is MINITAB. I will go into here. Let me copy it here. Okay, so okay, just take. So let me draw this graph. So again, go to this histogram, okay, and I will take C50, okay. So I have a perfect normal distribution. Perfect normal distribution. Okay, if you want to go execute the other along with the descriptive statistics, it is better. Sorry, basic statistics, the graphical summary. Okay, C15. I have to select. Then okay. You can see here. You can see here. P-value is 0.639. It is accepted. If you want to try whether each sample is exponential, that also we can see whether it is right. So you can see that mean is 10. So we started with the mean, exponential distribution with the mean. We generated a sample with a mean 10. So as you can see the population mean now is going to become the same. As per the central limit theorem, it is 10.5111. Okay, now let us now minimize this. Let us compute the descriptive statistics of this. Okay, so mean anyway is going to be here. Let us compute what is mean. So mean is a population related characteristics. Let us compute first. So population mean is equal to 10. So it is already done. And population standard deviation again is 10 because it is same. And SD by root n, SD by SQRT of n. Let us compute that also. That is equal to standard deviation divided by.
Share your screen, sir. Sorry.
Oh, okay. It's not coming as okay. Okay. I'm in Excel now. Sorry. Okay. Can you see now?
Yes, sir.
Excel?
Yes, sir.
Okay.
Yes.
Okay. So what I'm doing is I'm computing the population related statistics first. That is mean. We know what is mean. It is 10 because it started with exponential 10, and standard deviation is also 10. And standard error, what is going to be standard error now? That is sigma by root n, which is equal to this 10 divided by SQRT of the sample size was 20. So 2.3. Now let us go for the computation of, let us compute the mean. So I have the mean here computed already. So the means are here starting from BC4. Okay, so BC4. So let us compute the mean here. So that is, this is related, sample related statistics, sample mean. So let us say average of, BC3 to BC53. I hope so. Okay, so 10.49, almost fine. So both population mean and sample mean of means. This is actually mean of means. Please note, central limit theorem gives mean of means, the distribution of means. So this becomes mean of means, x bar bar. So 10.4. Let us compute the standard deviation also. STD of the same thing, BC3 to BC53. Okay, this is 2.824. So please note this. So this value and this value and the standard sigma by root n should match. Perfect. So this is what is the central limit here. Okay, let me also now quickly tell you, as I told you in the somewhere in the middle, that if you treat column wise, if they are samples, definitely row wise also there should be samples. So let us do some exercise on that. Okay, so I have some samples here. Okay, so this is your uniform sample. So I am now going to have to take a good sample. Okay, so okay, let us compute row wise. Okay, so here I am computing average of. So where did I start? I think it is, let me go again. average of this, that is actually D2 onwards. So please note that I have changed the nomenclature, actually speaking. Now earlier it was column wise I treated as samples. Now I am treating row wise as samples. So this is my sample mean of that row. Same thing I did it for all. So I have the sample means now. So I don't have to transpose this. I directly copy it. I will now share the MINITAB software. So here is the MINITAB. Okay, let me put it somewhere here. Copy, paste it. I will go back to the. Okay, so this is the last dialog box I called. I don't have to go every time graph, select histogram, etc., etc. Here is a dialog box. So let me again show you how it is. I can either go with a graph, histogram like that. You will get to. Instead, what I'm doing is, and this is my last dialog box. Because why should I every time I go to it? So I simply select C7, 17, and say OK. So I'm back to the, so perfect now. This is really a, so row wise also, so not necessarily that they will have the same value, because your sample size and number of samples are different, but both will give you the same conclusion. So this row wise also I can treat it as sample, and in that case sample size number changes, actually that is to be to see. So you can see that the population mean, the sample mean is now, mean of mean is now 29.95, it is almost 30, and p value is 0.51, perfect normal. Okay, so let us now, in the same way you can compute the mean over here, mean and the sample related statistics here. Okay, so please note that, let me compute the mean here, sample related. So let me say, sorry, I'll have to change the, so I am back to Microsoft Excel now. Please, anybody please say, okay, I am back to Excel now. Okay.
Yes,
yes, sir.
Yes, sir.
Okay,
Yes, sir.
okay.
Yes, sir.
So
That's fine.
now. Okay, so I'm now showing the sample related mean. So mean, that means mean of means. So what is that? Average of. Sorry. There are so many panels open here, so I'm finding it difficult. Okay, so where is the mean? Where is that mean gone? Sorry, mean I have to compute again here. That mean, and their mean has, I mean, pasted there. Okay, so average of, okay, let me again go back. Okay, so average of the whole sample. Since the random samples are changing every time, so it is nice to work with. So every time you will not get the same constant result, but approximations and everything will be same. So this is the sample. I will copy throughout. Okay, this is the sample. So about 300 something samples. Okay, and the mean of this sample, I will now compute. Average. So perfect, 29.94. Let me also compute the standard deviation of this. STD, standard deviation of this. And this, sorry, what happened? I don't know. Yes, okay, 1.74. Oh, perfect. Okay, you can see that it is 1.74. So what is the sample population related? The standard error is coming out to be this. So let us see what is the standard error. So we'll have to compute the standard error because sample size change here. Please note, it is not 32, which is something else. So I think it is correct. It is correct. Anyways, there's a cross approximation. Maybe I might have done something wrong somewhere. Okay, please pardon me. Okay, so this is how you will have to, you can go for the understanding of central limit theorem. So I hope whatever I just wanted to show you in terms of execution, I just over. So I will just get back to you with a presentation now. Presentation mode again. I just want to share 1 or 2 more slides with you. Okay, then we will conclude. Or will I will wait for 1 or 2 questions. So I am back to presentations now. So please tell me, one of you, are you back? Can you see the presentation again?
Yes, sir. Yes, sir.
Okay, good. So exponential distribution. So you can see different types, you know, exponential growth, exponential deterioration. The same way you can try with any distribution. I'm sure that you are comfortable with. But there are some limitations in Excel because you cannot generate samples from all the distributions. There are few distributions. Okay, so limited, very limited. Many, I mean, among the discrete distributions, only binomial, Poisson, Bernoulli possible, and among continuous distribution, you can have uniform, normal, and even exponential is not possible. So you'll have to go with that kind of technique which I had just shown you. Okay, so let me also invite your attention for 2 more slides. Okay, so please note that CLT is relevant at many places, and in mathematics also there are a lot of theorems where you work with sequence of numbers, sequence of variables, or you can say. So what is the sequence of, what is the limit of sequence of numbers after some certain stage? What is the force of attraction? What is the convergence rate, etc., etc.? In that case, again, this kind of theorem helps you a lot. So that's where the law of large numbers comes in. So big data related things I already mentioned you. And in the law of large numbers, there is, the central limit theorem is used especially for the sum of random variables like this. Okay, so accordingly, there are various versions. This I actually picked up from some research of from the internet. So they put central limit theorem in 2 different versions actually. So this is that means you can there is a characteristic function concept where characteristic function always uniquely define a distribution function. So with characteristic function, the second definition is about the characteristic functions. You can do even many often when you suppose you have 2 different variables, say 2 different populations. What is the sum of those 2 populations? What is the distribution? That is where the convolution concept comes. Okay, so in that case again, central limit theorem plays a very important role to find the distribution of that. And similarly, another fine thing about central limit theorem, when you work with Excel software or MINITAB software, is that you can come to know what is the ideal sample size, because this is most often asked in the question. What is the ideal sample size? Most often we say that if n is greater than 30, we say that it is large sample. If it is less than 30, it is small sample. Now, this concept can be very well justified if you work with central limit theorems like this. With that, I would like to stop here because we have already exceeded the timing of 1 hour or more. So I hope the presentation was good, useful. I invite 1 or 2 questions from the participants. So please work with Excel. That's why I specified I preferred Excel software. I used MINITAB software only for drawing the histogram, nothing else. I can do it in Excel also because there it takes time. This much, in this kind of environment, just specifically for 1 hour or so. So it's very difficult to show everything. So I request all the participants to work with different distributions and see the importance. And please understand the importance of the large sample size, means greater than 30 and less than 30, and what would be the ideal sample size. Okay, thank you very much for your patient hearing. Over to DK or Drupal.
Yes. Okay. There is one question from DMU. That is what is the device name written here. He's asking, he or she's asking, what is the main advantage of central limit theorem?
See, some of the slides I already told you. That just now also I told you. See, this question can be answered very well. What is the ideal sample size? What should be the ideal size of sample for getting into normal? See, we are trying to reach to normal. If you want to have your base distribution as normal, and if your sample doesn't allow it to be normal, but you can reach to normal through some kind of manipulation, I already told you. But this is one way. By central limit theorem, it is guaranteed that you will be reaching to normal. Only thing is you have to increase the sample size. So this is the main advantage of it. You are not working every time. You are not working with normal distribution. Most of the time you will be working with some unknown, with distribution having not even specified mean or standard deviation. So what you do with that case? You want to take some decisions about your process, about your product, about your service. What you do with that? So reaching central limit theorem is considered to be one of the fundamental theorem in statistics. Convergence theory, you can know how the things goes up. So n tends to infinity means that makes a lot of sense. That's why I've shown you in the illustration also. Row wise also I can treat it as sample, column wise also I can treat it as sample. So both way, if it goes going normal, so you will get advantage. The sampling, if you take only one sample, things are not going to make anything sensible. So you have to do the sampling. If it allows, in many industrial experiments or experimental research, you may not be in a position to experiment it with the data every time, but you should see the ways and means how things can be done. Sampling, if sampling is possible, then do the sampling. Then the advantage here is that you can get into normal easy. Thank you. Next one.
There is a question from Endel Ali. I think if Endel Ali is able to hear me, you can unmute your mic and ask the question to the speaker directly.
Okay.
Yeah, thank you. May I ask you?
Yes, please carry on.
Yeah, thank you. In some cases, data may not be normal, and I told that it's better to test the normality using some graph you have shown us, the histogram and many other graph. Yeah. So, yeah. But some statistician or some scientists recommend that it's not only possible to use this graphical. You have to look for other inferential methods. So, as professor, which is statistical test do you recommend us so that to test this normality? Thank you.
First thing is you talked about the normality test. There are many tests for normalities. Okay. Now, testing for normality is also a way of confirming whether your data is good or data has some quality or not. This is first point.
Sure.
Right? So, yeah, you carry out a test procedure, but even when you carry out a test for normality, again, looking at the p-value only, you will have to decide whether it is normal or not. If p-value is very small and you cannot decide whether it is normal, definitely you will have to have some kind of manipulation further. You may have to go for standardization, normalization, or some other procedures. Right? So, as such, there is no hard and fast rules to say that this is the best way to get into normal. There's a trial and run method you should carry out first.
Thank you, sir.
Welcome.
I think one last question, if anyone has, we can.
There is one question from why 30 is the norm. Muralidharan sir.
Yes, I'm here.
Why greater than 30 is the last sample? Means what is the significance of that 30 number?
That's very, very important. You can say that's a number, a special number for statisticians and statistics. 30. So see, that's why I shown you, illustration. I started with a small sample first and large sample then. You see, you could have seen the difference. When you work with a small sample, naturally, the variations will not be accounted for. You want to account for the complete variation lies within the data. And that can be done only if you increase the sample size. So number 30 is a very unique number, no doubt. And so again, there is no specific theory says that it should be 30 or larger than 30 conservatively, etc. It's a number which is generally treated for making as a good approximation to normal. No other base, nothing else. And sample size calculations are available for different sample, different ways you will have to see. Even if when you change, see in the case of exponential distribution, my a small, relatively a small sample, through that I could reach to normal. Whereas in the uniform case, in one case it was a very large sample. Then only then I could see get into the normal. So depends on the situation, also depends on the sample population, sampling population also. So from where you are sampling. So sometimes small sample may be enough, sometimes large sample may be enough. Okay, it's a subjective actually. Thank you.
I think then we can end the session now.
Thank you very much, madam.
Yeah.
Please ask the participants to have their feedback or their liking or this thing, etc.
Yeah, the feedbacks are continuously coming in through the chat. Yeah.
Okay, they can also communicate with me directly on my email. That email I had already shown you. The participant, the first slide, it is there.
Okay, so once again you can just put the first slide, sir, so they can.
Here is the first slide.
Yes.
Here is the first slide.
So here is the mail ID of the speaker.
All are welcome. Yes.
The official as well as his personal email ID. So you can communicate with him for more guidance or some more question or query. With this, I would like to thank, first of all, the Honorable Dean, Faculty of Science, for his cooperation. I also thank the Head Department of Statistics, Professor Vipul Kalamkar. I also, of course, thank Professor Muralidharan and all the participants. Without you and your participation, this would not have been possible. So thank you all. Thank you. Have a good day.
Thank you very much.
Thank you.
Thank you. Thank you so